Welcome to ICP-USA's webinar on top trends and architecture patterns for industrial automation in 2026. My name is Erica O'Hara, and I will be your guide through today's session. Thank you all for joining us, whether you're a data center operator, IT professional, or industry enthusiast. We're thrilled to have you here. By the end, you'll gain actionable insights to optimize your operations, reduce costs, and future-proof your setup. For those new to ICP-USA, we're a leading provider of industrial automation and data acquisition solutions, specializing in reliable, innovative products that empower critical infrastructure. With over 30 years of expertise, we've helped facilities worldwide achieve maximum uptime, energy efficiency, and proactive monitoring. Oh, another thing I wanted to add, we offer fast service, free tech support, free software, quick shipping, and a solid warranty to back it up. Our products are RoHS compliant and ISO 9001-15 certified. So here, the instruction, we've progressed from mechanization in Industry 1.0 through electrification, computerization, and the connectivity of Industry 4.0. Now, Industry 5.0 emphasizes human-AI collaboration, where humans and intelligent systems team up for more creative, resilient, and personalized production. This shift puts people at the center, leveraging AI to enhance, not replace, human ingenuity. The key drivers fueling this transformation include sustainability through eco-friendly practices and resource optimization, efficiency via AI-driven processes that streamline operations, and resilience in the face of supply chain disruptions, as we've all witnessed post-COVID. These elements are reshaping industries, making systems smarter and more adaptable. At ICP-USA, we're at the forefront with our data acquisition modules, IoT solutions, and automation tools designed to support this human-centric approach. The visuals here illustrate the interconnected future we're building. With that foundation, we'll dive deeper into the trends and technologies driving this change in the next sections. So ICP-USA stands out as an exemplary provider of data acquisition systems, programmable controllers, and IoT solutions that effectively bridge theoretical concepts to practical applications in industrial automation, supporting Industry 5.0 by enabling seamless human-AI integration through reliable hardware like remote I/O modules, embedded controls, and wireless communication protocols for data-driven decision-making and system optimization. Before we jump into the details, let's outline the agenda for today's webinar on the future of automation. This will give you a clear roadmap of what we'll cover. First, we'll discuss the future of automation, exploring emerging trends and how they're reshaping industries. Next, modern architecture patterns for smart facilities, diving into hybrid cloud edge designs and scalable systems for intelligent operations. Then, protocols for future-proof systems, focusing on standards like Modbus, OPC, UA, and emerging protocols to ensure interoperability and longevity. After that, the next-gen automated system technologies, highlighting multi-agent AI, confidential computing, robotic advancements, and more. We'll move into practical deployment strategies, a step-by-step guide with best practices, risk mitigation, and integration tips, followed by real-world case studies, sharing success stories from manufacturing and logistics to illustrate these concepts in action. And finally, we'll wrap up with conclusion and QA, recapping key takeaways and opening the floor for your questions. Starting with AI agents for cognitive tasks. By 2026, AI agents will take on complex cognitive functions in industrial settings like real-time data analysis, autonomous decision-making, and adaptive learning. This goes beyond traditional automation, optimizing workflows in ways that boost efficiency and responsiveness. Next, generative design for optimized production will leverage AI to create innovative designs that minimize material use, maximize efficiency, and enable rapid prototyping. This leads to customized manufacturing solutions perfectly tailored to specific needs, reducing waste and speeding up innovation. Then the integration of quantum computing for complex simulations. Quantum tech will allow ultra-fast simulations of materials, processes, and supply chains, solving optimization problems that classical computers simply can't handle efficiently. Imagine redesigning entire production lines overnight. We also see the rise of humanoids and robotics. Humanoid robots will integrate more deeply into production lines, handling dexterous tasks alongside humans. This enhances flexibility and safety in dynamic environments such as assembly and quality control. Finally, a strong sustainability focus, for example, on energy efficient systems. There will be an emphasis on green technologies that include energy efficient automation to reduce carbon footprints. This involves optimized resource management and renewable integration for eco-friendly operations. Faster decision making. Automation powered by AI will speed up data-driven decisions in manufacturing. This means real-time adjustments that enhance productivity and cut down on errors across entire operations. Imagine analyzing sensor data instantly to optimize assembly lines, no more delays for manual reviews, reduce downtime via predictive analytics. In the energy sector, tools like these will forecast equipment failures well in advance. This minimizes unplanned outages, extends the lifespan of assets, and allows for proactive interventions, keeping everything running smoothly and cost effectively. Scalable operations in manufacturing, energy, and logistics. AI-enabled systems will make scaling effortless, from accurate demand forecasting in logistics to adapted production lines in manufacturing and efficient smart grid management in energy. This flexibility is crucial for handling growth or fluctuations without major overhauls. On this slide, we show the transition from Industry 4.0 to Industry 5.0. Industry 4.0 is represented by automation, smart machines, and connected systems. The main goal was efficiency, speed, and data-driven production. Industry 5.0 builds on that foundation, but adds a stronger human focus. The slide highlights collaboration between people and machines instead of full automation. It also shows values like sustainability, resilience, and worker well-being. From our perspective here at ICP DAS, this shift means systems must be designed differently. Automations don't matter, but it must be flexible, safe, and supportive of human workers. Our hardware and communication solution helps customers make this transition in a practical way. So this slide here shows how modern smart facilities are built using layered system architectures. You can see edge devices placed close to machines and sensors, with cloud systems shown at a higher level. This layout represents how data flows from field to higher level systems. At the bottom of the slide here, field devices such as sensors, I/O modules, and controllers collect real-time data. These devices handle immediate control tasks locally. This reduces latency and allows systems to keep running even if network connections are unstable. At the top of the slide here, the cloud layer is used for monitoring, data storage, and analysis. This separation allows facilities to gain insight without affecting real-time control. At ICP, we design products that fit naturally into this kind of modern architecture. The overall advantages of using modern architecture patterns rather than focusing on a specific technology. The first benefit highlighted is flexibility. Modern architecture patterns allow systems to adapt more easily as requirements change without needing a complete redesign. Another key benefit is scalability. These patterns make it easier to grow systems over time, whether by adding new features, users, or integrations without impacting existing functionality. The slide also emphasizes reliability and maintainability. By using well-established patterns, systems become easier to manage, troubleshoot, and upgrade, reducing long-term operational risk. This reinforces why modern architecture patterns are preferred. They reduce complexity, support future growth, and help organizations build systems that last. The key industrial communication protocols that help build future-proof automation system. OPC UA provides a secure, scalable, and vendor-neutral framework for data exchange from the factory floor to enterprise systems. Ethernet IP enables high-performance real-time communication between PLCs, I/O, sensors, and power monitoring devices. Profinet and Profibus support reliable deterministic networking for both modern Ethernet-based and legacy field bus environments. Together, these protocols ensure interoperability, flexibility, and long-term system readiness as industrial networks continue to evolve. The key selection criteria for building future-proof industrial systems organized across scalability, security, AI, and edge compatibility, and low latency performance. On the left, we compare how OPC UA, Profinet, and Ethernet IP scale from embedded devices and legacy systems all the way up to enterprise and smart factory environments. Below that, the security section highlights built-in encryption, authentication, and deterministic protections designed for today's interconnected IIoT networks. On the right side, the focus shifts to compatibility with AI and edge computing, showing how each protocol supports real-time data access and analytics without disrupting control operations. The low latency section emphasizes deterministic sub-millisecond performance, ensuring these protocols can meet the timing and responsiveness demands of modern AI automation systems. Here we show practical strategies for building future-proof systems. On the left, we start with prioritizing vendor-agnostic protocols, highlighting how open standards reduce vendor lock-in, lower term costs, and make it easier to scale across multi-vendor environments. OPC UA, Profinet, and Ethernet IP are each called out for their role in enabling secure cross-platform communication while supporting both legacy and modern hardware. On the right side, the slide shifts to migration strategies, outlining a phased approach that includes infrastructure audits, protocol converters, and pilot testing to minimize downtime. Each protocol is shown as a bridge from legacy systems to modern Ethernet-based networks, helping organizations move toward Industry 4.0 without disrupting existing operations. Okay, so let's talk about some of the key emerging technologies that are shaping the next generation of automated systems. First, we have multi-agent AI systems. These are modular AI agents that can work together on complex tasks. We can think of them as specialized digital teammates, each focusing on a specific function but collaborating intelligently. This allows for scalable automation in industry like supply chain management or IT operations, where coordination across multiple systems is critical. The AI native platforms, unlike traditional software environments that later integrate AI, these platforms are designed with AI at their core. They support high performance computing and adaptive digital foundations that make automation not only faster, but more responsive to real-time data. We have here confidential computing. So as automation becomes more data-driven, security and privacy are major concerns. Confidential computing ensures that sensitive data can be processed securely, even in shared or cloud environments. This technology uses hardware-based protection to safeguard information during AI analytics and cross-company collaboration. Finally, advancements in robotic and vision systems. Here we see physical AI in action, combining sensors, machine learning, and computer vision to give robots and smart equipment the ability to perceive their environment and make autonomous decisions in real time. These technologies working together are enabling a new era of intelligent, secure, and adapted automation across industries. Let's explore how these innovations come together in an integration roadmap. So first we have the IoT combination for hyper-automation. By combining IoT sensors and continuous data streams with automation tools like robotic process automation or RPA and process mining, we can create truly self-optimization systems. These systems don't just collect data, they interpret it in real time to enable predictive maintenance, intelligent workflow orchestration, and responsive industrial operation. Essentially, IoT becomes a sensory network while automation tools act as the responsive nervous system that adapts and improves continuously. We move into the agentic AI focus for autonomous operation. This takes automation a step further by using autonomous AI agents, systems that can reason, plan, and take actions independently. Instead of just reporting issues or waiting for human input, these agents make proactive decisions in real time, such as adjusting supply chain processes, managing exceptions, or rerouting workflows to maintain efficiency. It's the natural evolution from IoT as a data collector to IoT as an intelligent decision maker. At the bottom of this roadmap, you'll see the emphasis of our ICP DAS USA integration. Though our IoT management software, wireless data acquisition tools, and SCADA system, we're building the pathway that make the integration possible, bridging sensor networks, AI, and automation into a cohesive agent-driven ecosystem. As we look toward 2026, we're sending a rapid acceleration in the adoption of next generation automation systems, particularly across warehouses and industrial environments. Organizations are scaling their AI-driven initiatives from pilot projects into full production environments driven by measurable gains in efficiency, quality, and real-time responsiveness. Widespread adoption in warehouse and factories will be fueled by the integration of AI-enabled quality control, predictive maintenance, and smart manufacturing systems. By 2028, approximately 80% of warehouses are expected to utilize some form of automation, with 2026 identified as a turning point where operational efficiency and resilience begin to converge. As shown in the chart, the warehouse automation market is projected to grow from about 25 billion to more than 100 billion by 2035, reflecting significant investments in robotics, machine learning, and data connectivity. On the enterprise side, about 15 to 20% of organizations are expected to advance toward true automation maturity by enabling agentic AI frameworks, systems capable of autonomous reasoning and task execution, while nearly all enterprises are exploring AI implementations. Only a few are making the necessary investments in data foundations and process optimization required to scale these capabilities effectively. So the first step is to assess needs. This involves performing a detailed evaluation of existing operation processes, looking at ROI potential, risk exposure, and efficiency gaps. We conduct opportunity assessments to pinpoint where automation can yield the highest value and to define the metrics that will guide integration success. Another practical deployment, building roadmaps. That means setting clear objectives, aligning automation goals with business outcomes, and designating project owners or champions across departments. This phase often includes designing pilot projects for quick wins, which demonstrates return on investment early and build organization monument for broader rollouts. Reinforcing infrastructure. So this step is about ensuring network reliability, system compatibility, and scalable hardware that can handle real-time automation demands. Robust data connectivity such as high bandwidth Ethernet and PoE-enabled networks is critical for supporting edge devices, IoT sensors, and AI-driven processing at scale. And finally, we adopt lean project management. A lean approach allows organizations to start small, implement automation with minimal disruption, and continuously refine performance through iterative feedback. By applying data-driven monitoring, adjustments can be made quickly to fine-tune systems effectiveness. As we move from planning to execution, these best practices ensure reliable and scalable automation deployment. So you start by using standardized communication layers, consistent protocols, and integration framework help streamline data flow between systems and simplify interoperability. Next, implement scalable pipelines, design flexible data and process architecture that can handle growth, focusing on high-value workflows and iterative employment for adaptability. Train teams early to build technical competence and user confidence, ensuring smooth adoption of AI and automation tools. Finally, monitor performance through data ops. Continuous monitoring and data quality assurance keep automation systems optimized and responsive as workloads evolve. Practical deployment risk mitigation. The best approach is to start small with pilot projects, allowing teams to test systems, collect feedback, and make adjustments before expanding organization-wide. It's also critical to budget for cybersecurity, ensuring that access controls, data validation, and infrastructure protections are in place. And finally, measuring ROI through KPIs such as downtime reduction, efficiency improvements, and cost savings helps track performance and guide continual risk-based refinements. Real-world case studies, AI in manufacturing. Okay, so this case study highlights how AI is transforming manufacturing operations through predictive maintenance. In this example, a major automaker deployed agentic AI systems to continuously monitor productive line equipment and predict potential failures before they occur. The AI analyzed sensor and vibration data to identify anomalies, triggering proactive maintenance and minimizing disruptions. As a result, the company achieved a 30 to 35% reduction in unplanned downtime, significantly boosting productivity and operational efficiency. These improvements translated into an annual cost saving in millions and enhanced overall equipment reliability. Similarly, ICP DAS USA's vibration monitoring systems and smart power meters enable comparable AI-driven predictive maintenance strategies in modern manufacturing environments. The key lessons learned from real-world automation and AI deployments. One major takeaway is the importance of scalability through standardized communication protocols such as Ethernet IP, Profibus, and OPC UA, which ensures seamless system integration and feature expansion across devices and networks. Another insight highlights the return on investment from next-generation technologies, with AI and edge computing delivering up to 50% downtime reductions and significant operation cost savings. Additionally, it's crucial to develop strategies for overcoming integration challenges, starting with pilot programs, ensuring data quality, and properly training teams for long-term success. The key takeaways from AI and automation in manufacturing and logistics It projects that by 2026, the integration of agentic and multi-agent AI systems will become widespread, enabling full autonomous and predictive operation that significantly improve efficiency. The emphasis on protocol flexible architectures underscores the importance of standardized hybrid edge cloud systems that ensures seamless scalability and communication between devices and platforms. Furthermore, deployment-focused strategies encourage organizations to begin with pilot projects, strengthen cybersecurity practice, and measure ROI to ensure sustainability digital transformation. Thank you all for joining us today. And if you need help find a specific tailored solution for your application, our team can guide you through our solutions to find what best suits your need. You can check our website down here. Hope everyone has a productive day. Thank you.